Hi, in this video we'll go over integration testing. As you saw in the previous videos on software testing overview, the testing life cycle consists of unit testing as the first step, where an individual unit is individual units are thoroughly tested first, followed by integration testing. So this is where subsystems with the multiple units put together are tested to make sure that the interaction between various units is happening correctly, and that's followed by system testing and then acceptance testing. So today we'll focus on different strategies that can be used in order to perform integration testing. So here's an overview. We'll look at these different strategies called Big Bang, Bottom Up, Top Down, Sandwich, and continuous integration. So these are some of the different integration testing strategies. So basically the idea with the integration testing is that an overall software system could be a collection of multiple subsystems, and each subsystem could be a set of classes or units, and all of this is determined during the system and object design. So always in the software development life cycle, we always start with a requirements analysis, followed by a high level system design, followed by a detailed design which includes object design, and then the implementation is done, followed by testing. So the high level design provides the overall system architecture, and that's where it's determined how our system is broken up into subsystems and what goes into each of the subsystems. And then in the detailed object design, the design for each individual unit is determined. So our goal with integration testing is to test all of the interfaces between the subsystems and make sure that that interaction of the subsystems is working correctly. And that's what we're going to we'll see what are some of the different strategies, and when do we use a particular strategy over another strategy. So now, why do we have to do integration testing? Say we've done unit testing and we've made sure that the unit is working perfectly, but then we still need to do integration testing later on, because now this unit is going to be put into a subsystem, and then the subsystem is going to be part of an overall system. So the unit test might work, the unit might work in isolation, but typically a lot of failures happen when the interaction of subsystems begins. So and the reason for that could be sometimes we bring in off-the-shelf third-party components to fill in for certain parts of the subsystem. So there it's important to see if the units that we've developed are working correctly with those third-party components. Or sometimes some of these other components are built by other parts of the team or the project. So it's very important to see if it's the way the unit works and understands things. Is it the same as the way information is being passed by the other unit? So now if we skip integration testing, then system testing can be very time consuming, because then if you just test the overall system and it's working, and if failures happen, it will be very difficult to identify where exactly that failure happened and which part of the software system is it stemming from. That's the reason it's important to do testing in this particular order, wherein you do unit testing. Within unit testing, there's the static analysis of code at compile time, then the dynamic testing once the unit has been built, and then you get to integration testing to test the interaction of different units with each other and subsystems with each other, and then get to system testing. The goal, the hope is that a number of issues would have already been found in these previous phases, so there's going to be minimal issues when we get to that system testing level, and we want to save on our time and resources when we're doing that. So that's the reason integration testing is important. Each and every testing method in the life cycle are very important, because testing in general is a very expensive activity. So for integration testing, there are two key things that are needed, stubs and drivers. So basically a driver is basically, now say there is this particular unit that's being tested, that's the tested unit. Now driver is a component that calls the tested unit. So say the tested unit provides some functionality, the driver class needs that functionality, so it calls those methods of the tested unit and uses them. So it's possible in a number of cases that these the classes that call the tested unit are still not ready, but then we need to do our integration testing, so that's where we write what are called drivers in order to mimic the functionality of that upper class. Stub, on the other hand, is a component that the tested unit depends on. So basically the tested unit calls methods of the stub, and because it needs some data or information. So again, same thing, sometimes the stubs or these lower classes may not be ready, or they might have so the idea is to mimic that functionality through some kind of partial implementation or by returning fake values. So at least that interface, our idea is to test these interfaces and make sure that they're talking correctly to each other. So a number of times stubs and drivers are needed and are implemented with this fake or partial implementation, or trying to mimic the implementation, and later when the real classes or real subsystems are ready, then we replace these drivers and stubs with the actual implementation. So we will be using this terminology stubs and drivers a lot in this lecture. Now let's consider this design, a 3-layer design of a spreadsheet. All of us are familiar with spreadsheets and use it in our daily life. So look at this 3-layer design, wherein the first layer is kind of the UI layer, the second layer is our business logic layer, and then the third layer is our data, the data layer. So the idea is, in the layer 1 we have our views, we have the spreadsheet view. So this is a high-level system design. It's a system design, so it's showing all of the systems and the subsystems. So and you see that they're numbered with the letters A through G. So our first subsystem is a spreadsheet view, and it's in layer 1. It basically pertains to all of the user interface of the spreadsheet. Then in layer 2 we have an entity model, calculator, and a currency converter. We have 3 subsystems. And then in the lowermost layer, in layer 3, we have things related to the data. The binary file storage is subsystem E, XML file storage is subsystem F, and then a currency database is subsystem G. So basically the currency converter depends or calls currency database in order to get information about currency conversion. So this is where all of that information, the currency database is the one where all of that information is available. Now the spreadsheet view in turn calls currency converter in order to do some calculations, and the results are returned to the spreadsheet view, and the purpose of the spreadsheet view is basically displaying it in its view. Same thing with calculator. It calls the calculator to do certain mathematical calculations, the results are returned to the spreadsheet view to display them. So we will use this example in understanding the different integration testing strategies. So we will refer to them using just the names A, B, C, D, E, F, G hereafter. So the first strategy for integration testing, it's called the Big Bang approach. So basically now we have all of these subsystems A through G. So we need to test them. So the assumption is that those individual units, all of the individual classes within each of these subsystems have already been tested through unit testing. So they've been tested in isolation. Now we want to make sure that the subsystems put together are working. So in the Big Bang approach, the idea is to just test each of the subsystems first. So test A, B, C, D, E, F, G individually. So that's the first step, and that can happen in parallel. Each of them can be tested concurrently as they're getting developed. So the idea is when we test A, all of the subclasses within that are individually tested and their interaction is tested. But here we want to see how all of these subsystems, when put together, what kind of strategy do we use to test it. So in Big Bang, the idea is to just test all of the individual subsystems and then put them all together into the overall system and then test the overall big system with A, B, C, D, E, F, G put together. That's the reason it's called Big Bang. But then, as you can see from the way it's done, it's really not the most effective way to do integration testing. Let me pause there for a couple of seconds and let you think why. So what is missing? So with this kind of testing, what is not getting tested? So if you look closely at this diagram, if you see the workings, so because we tested the individual units and then we just put the whole thing together and tested the overall system, the individual integration of B, E and F did not get tested. The individual integration of D and G did not get tested. And then the individual integration of A and C, the interaction between A and C is not getting tested. The integration between A, B, C and D is not getting tested. So there are so many parts that are not getting tested, and we're straight away getting to the entire system. So there could be a number of issues still, underlying issues in there that'll show up later in system testing. So that's the reason it's not an effective approach in most cases, especially when we have a layered system design of this kind. Bottom-up testing strategy. So in this strategy, the subsystems that are in the lowermost layer of the hierarchy, those are the ones that are individually tested first. So we're going to start at the bottom and then work our way upwards. So once all of the systems at the lowermost level are tested individually, then we include the next subsystems from the next layer, and then we keep working our way up. So we do this repeatedly until all of the subsystems in the hierarchy are included. So with this strategy, what we need is drivers. A lot of drivers have to be written, because when we start at that bottommost layer, then we don't have any of the subsystems that are above it. So any of the systems that use these other subsystems are not available, and so in place of those, we have to use driver programs, which are basically making these fake calls to the subsystem. So here's how the bottom-up integration would look with the example that we have been using. We'll start with the lowermost layer, so which is E, F and G. So we test those first individually, as well as C actually, E, F, G and C. All of these four, because they are the leaves in this tree hierarchy, those are the ones that get tested first. Then once that's done, we start including the next layer, the subsystems that's just right above it, so which is B, E, F. So we basically test these interfaces, and if the connections between B and E and B and F are working correctly or not. And then the next one is D and G. So that subsystem gets tested, and then once that's done, so we are done with the lowermost layer and then the middle layer, and then we move to the top layer, so which is basically the entire subsystem. So that's the entire A, B, C, D, E, F, G all put together. So that's called the bottom-up integration strategy. So as any other strategy, there are pros and as well as cons of this bottom-up testing procedure. So the cons are that the testing of the most important subsystem, usually the most important subsystem is considered to be the topmost layer, the user interface, because that's the one that the users are directly interacting with. So that's the one that's exposing the main functionality or features of the system. And with this strategy, that's the layer that gets tested at the very end. whereas it's considered the most important. The second disadvantage is that a number of drivers are needed and drivers have to be written. But on the other hand, the pros are, the advantages are that stubs are not needed. There's no stubs needed at all in this case, and typically you need stubs when the lower the systems that the current unit that's being tested, whatever it depends on or relies on or has to make calls to get some information, when those are missing, then stubs have to be written. Stubs are harder to write because it's hard to provide partial implementation, and then fake values have to be created to mimic that system that's missing. So in this case, the advantage is that there are no stubs needed at all. Typically, this kind of a strategy is useful for object-oriented systems where the entire structure of the software is in terms of objects. It's also useful for real-time systems, and then systems where there's strict performance requirements. And the reason it's useful for these three kind of systems is because like you saw, we're starting at the lowermost level, and typically wherever there's strict performance requirements or in real-time systems, in order to make sure that the systems are efficient, we have to make sure that the lowermost layer is efficient. Performance usually, typically the lowermost layer is the one where the data is stored, so it's kind of the database layer, and when there's strict performance requirements, it has to start at that layer. We have to make sure everything's efficient there, and then work our way from there and on. Same thing with object-oriented systems. We have to make sure that our single units work correctly and efficiently first. So it's useful there, and with real-time systems where again the interaction is happening in real time and it has to be quick and responsive, again over there as well, bottom-up strategy is a great way to go. So those are some of the pros and cons of the system. But like we saw, the disadvantage is that the most important subsystem is tested last. So can we do better then? Is there something else that can be done? So here's the next strategy, which is the opposite of bottom-up strategy. It's the top-down strategy. So in this case, we're going to test or start with the topmost layer, which is which is kind of the controlling or the most important subsystem, and then we will combine all of the other systems and work our way downwards in the reverse order. And again, we do this until all of the subsystems are incorporated into the test. Now in this case, it's the reverse of bottom up, so we don't need drivers in this case, but we need stubs, because at every stage, the systems that are below which are providing some kind of information or service is not available. So we need stubs in order to mimic it. So let's see how this looks. Again, with our example system, which is structured in three levels, 3 layers, we're going to start at that topmost layer, layer 1. So A, the subsystem A, is tested individually first. Once that's done, then we include the next layer, which is B, C, and D. So when that's included, what we have now is the subsystem A, B, C, D together. So that's layer 1 plus 2 together. So that's tested. And then once that's done, then we include the next layer. So basically there's only 3 layers here, so we include this. So now what we have is this entire A, B, C, D, E, F, G system with all of the 3 layers. So that gets tested. So here, when we're testing A individually, we need stubs to mimic whatever B, C, and D, whatever services B, C, and D were providing to A. So A is probably making calls, some kind of function calls to B, C, and D to fetch some data or some information. So that needs to be mimicked through stubs. Similarly, when we are dealing with the subsystem A, B, C, D, some information is probably needed from E, F, or G. So that needs to be mimicked through stubs. So let's look at the pros and cons of top-down integration. So the pro is that the most important layer, which is the user interface, and that's where all of the functionality, it defines the functional requirements of the system. So that's getting tested first. So that's very good in terms of making sure all of the requirements are met. The second advantage is that drivers are not needed, so that's an advantage. In terms of cons, the disadvantages are that a lot of stubs are needed in this case, and writing stubs is usually difficult, so there's that additional work that has to be done, and sometimes it's not even possible to test all kinds of conditions with stubs, or the stubs need to be written in such a way that all of the conditions are can be tested. And then a large number of, in this case, like you saw in the example, a large number of stubs are needed to ensure that all the lowest level systems, methods are all mimicked and provided. So that's the big disadvantage with the top-down approach. But then having said that, in this case, actually there's another disadvantage is that some interfaces are not tested separately. So, and let me specifically show you that. So as you saw, when we went from layer 1 to layer 1 plus 2, we tested A, and then we directly tested A, B, C, D all put together. We did not test the individual interfaces, the individual interface between A and B. We did not get to test that. We did not get to test A and C separately by itself, and then we did not test A and D separately by itself. And there is a whole lot of value in doing that, because now we're testing the entire A, B, C, D together, and if there are issues, it's going to take a little longer to debug, because now we don't know where the issue is. Is it in the AB interaction, or AC interaction, or AD interaction? So in a similar manner, when we go from this second layer to the third layer, where all the layers are included, we are not testing BEF interaction. So some of those individual interfaces, even D and G, is not getting tested by itself separately. So some of those individual interfaces are getting left out, and that's another big disadvantage with the top-down strategy. But then having said that, top-down strategy is very useful for systems that are heavy on user interfaces, that are heavy on the functional requirements, and a lot of functional requirements where user is interacting with them. So in those cases, this is a good strategy to go with. So now, can we do better and take care of some of those disadvantages that were there in this previous system? Mainly, some of those interfaces, individual interfaces, not getting tested. So the next strategy is a sandwich testing strategy, where the idea is to combine top-down and bottom-up strategy. So we get the benefits of both. We want to somehow combine the top-down and bottom-up strategy. So the way it's done is that the entire system is viewed as having 3 layers, and those 3 layers are, there is a target layer. A target layer is identified, and this target layer is typically somewhere in the middle. So if it's a three-tier architecture, then obviously the second layer, the second tier, is going to become that target layer. But then if it's say a 5-tier architecture, 4 or 5, then we'll have to pick the middle layer as the target. Once we have that target, then the upper, so there's 3, we're going to look at it as 3 layers. So we're going to then have the upper layer that's above the target, and the lower layer that's below the target. And the idea is that the testing must converge at that target layer. So let's see how this looks. So we're going to use that same system that we have with the 3 layers. So we're going to do both top down and bottom up at the same time. So what that means is all of the systems in the upper layer are individually tested, and all of the systems in the lowermost layer, the bottom layer, are individually tested. So we test A, E, F, and G individually. So we're doing now both the part of top down, and then we've taken bottom up as well, and individually test all of those systems. Now once we're done with that, our next thing is to now converge with the target layer, and in this case, here's our target layer, that middle layer. So we want to make sure the upper layer converges with target, and then the bottom layer also converges with target. So what that means is A is put together with B, C, and D, and that subsystem is tested, and then EF converge with B, so the subsystem BEF is tested, and then G, the subsystem D and G is tested. So we have this middle layer, we had some subsystems here, we had some subsystems here. So now we are, after individually testing all of these, now we're converging any connections that they have with the middle layer, those are tested. Once that's done, then we basically put the entire system together and test the overall system. So the entire A, B, C, D, E, F, G put together is tested. So that's called the sandwich testing strategy. So the nice thing about this is that both the top and the bottom layer tests can be done in parallel. So if you have a system where our topmost layer with heavy user interfaces is important and that gets tested first, and say performance requirements are also strict, then the bottom layer also gets tested. So both of them are done in parallel, and then we converge with the middle layer. So the problem though here is, again, it still does not test some individual subsystems and their interfaces thoroughly. So still some interfaces are getting left out in this case. The problem that we were able to solve is that we're now looking at both the most important layer and then our data layer, which is important for performance. So we're doing both of them in parallel. So we've solved that issue. But then there are some interfaces that are still getting left out. And then the solution for that is then another strategy called the modified sandwich testing strategy. So let's take a look at that. In the modified sandwich, basically what we're doing is in parallel, we first test the middle layer with drivers and stubs. We test the top layer with stubs alone and the bottom layer with drivers alone. So say we have these, we have this three-tiered architecture. In sandwich, we were just testing the top and bottom individually, but now what we're going to do is test that middle layer also individually. In order to test the middle layer individually, we'll need both drivers and stubs, because the top, calling systems are missing, and then the systems from where you need information is missing. So both drivers and stubs have to be written. And then the top layer is tested with stubs, and the bottom layer is tested with drivers, because those parts are missing. Now once this is done in parallel, then the top layer that's accessing the middle layer. So basically we replace these drivers with that topmost layer, and then we replace the stubs that this middle layer was using, we replace that with this lower layer. So so that way now we're putting the entire system together and then testing it. So so the way it's done is, so we test all of the subsystems individually. If it's in the topmost layer, like in the case of A, we use stubs. In the case of B, C, and D, we use both drivers and stubs. And in the case of E, F, and G, we use drivers. So once that's done, then we start putting, we replace the drivers and stubs of the middle layer with the actual systems. So we basically put A, B, C, D together, that's this part, putting the, connecting the upper layer with the middle layer. And then B, E, F is put together, so connecting the middle layer with the lower layer, and then the same thing with D and G, that's this one. Now once that's done, then we put the entire entire system together to test the whole system. So in this way, we are trying to maximize testing all of the individual interfaces properly. That's the idea. So that's the modified sandwich testing, wherein all possible, so this is the kind of strategy that can be used where functional requirements are user interface heavy, and so that top layer is important, where the performance requirements are strict or it's a real-time system, so the bottom layer is also very important. And then we want to make sure all of the individual interfaces are tested individually. So that's when we go with modified sandwich strategy. One has to choose this strategy carefully, because a certain strategy has more work, like modified sandwich involves a lot more work because there's lots of drivers and stubs that need to be written in order to test those each of those layers individually. So it's a lot more work. So this strategy should be chosen only if those requirements are such that it's needed to test all of the systems, subsystems so thoroughly. Otherwise, we could go with one of the previous ones, with a top-down or a bottom-up or a regular sandwich. It all depends on the kind of system that we are testing. The next thing that we'll look at is continuous testing. So typically these days the idea is to continuously, as we're building, developing code and adding code, we're continuously testing as well. And the way it's done is basically to have a process set up such that continuous test and build can happen. So we want to be able to build from day one, test from day one, integrate from day one. What that means is that the system is always runnable from day one. When we start writing the first line of code, first we set up the process in such a way, the servers are set up in such a way that you start with writing a test that fails, and then write the code to make that test pass, and then have our build script such that whatever is there gets built and it gets deployed onto the server. So we have a running system at any point of time. Anytime a change is made, a new code is added, same thing, corresponding tests should be there. It should immediately get built and then integrated with the rest of the system, and the system should be runnable. That's the idea of continuous testing, and the tests should be set up in an automated manner, so that the tests get run automatically whenever a build happens. So the build happens, and automatically all the associated tests are executed to make sure nothing fails, nothing that was previously working now fails because of the new changes. So that's the idea. And in order to be able to do this, we need integrated tool support. So, and there's a lot of tools available that support this. We need a continuous build server. So there's multiple build scripts that are used these days, that will be covered in subsequent courses. We need automated tests with high coverage. They should cover as much code as possible. So that's done with the automated testing. And then there should be tool support for refactoring. Our IDEs provide for that. Whenever some code is refactored, then we automatically want to rerun all of our tests and make sure everything is still working. Software configuration management and source code management tools are very important, so we can keep track of any of the changes that are happening. And then issue tracking tools are available to keep track of any issues that come up and their status, and when they get fixed, and how they got fixed, and what was the issue and what caused it, and so on, so that in the future, if the same thing happens again, there's sufficient documentation to look up and see what had happened or how it was fixed previously. So with tool support, all of this becomes easy, and continuous testing is the way to go. So if we look at the continuous testing strategy, for the same example that we've been looking at, the spreadsheet example, which is designed with 3 layers. The top layer is the spreadsheet view. The second layer holds the business logic. It has the data model, the calculator, and the currency converter. And the third layer is our data layer. So in this case, if we followed the continuous testing strategy, it's pretty much, say on day one, if a small part of the spreadsheet view gets implemented, then that should, so basically that gets implemented, it's tested, and then it's integrated with the system, and it's deployed onto the server, so it is runnable, and it can be executed and seen if everything's working fine. Now next, say we add the functionality of cells and then addition. So basically cells are added by adding some functionality to the data model subsystem, and then the addition feature is included by adding the part of the functionality of the calculator subsystem. So now you see that we're further adding to each of the layers, to the different subsystems. So but then as these changes are being made to different subsystems, we want to make sure that it's all integrated. So we don't wait for 2 weeks or 3 weeks to do one big bang integration. That's never a good idea. The idea is to, as code is added, we test it, build it, and integrate it with the rest of the system that's already deployed on the server. That's the goal. Then say we add some features to the file storage, so to the binary file storage subsystem, and that's also integrated into the existing system. And then we continue developing each of the different subsystems individually in this manner using the continuous testing strategy. So it's very important to have automated tests set up, because that helps in checking if later when some new code gets added, it helps to test and make sure that whatever was previously implemented and working, that still remains working correctly. Nothing does it have some effect on the previously existing code, and we want to make sure that doesn't happen, and if it happens, then we want to know so it can be fixed. So that's the idea with continuous testing and automation. So the steps to be followed in integration testing is, first of all, the first and foremost is based on the kind of system and the requirements. One has to choose an appropriate integration strategy, the approach that will be used. And then based on that strategy, we're going to select the components to be tested. Now, all of the components have to be unit tested first. That's a given. Unit testing has to happen first. Once that's done, then based on the strategy, we put selected components together. And then any preliminary fix-up, that is, for the missing parts, drivers or stubs have to be generated. So that's step 2. Then we have to test. So what are we testing when we put these systems together? What are we testing? We're testing all of the functional requirements. So test cases have to be written, and all of the functional requirements are tested using those test cases. And those test cases are specific for that selected component or components. Then we test the decomposition of the system. So this is where we check all of the dependencies. So the test cases have to be written so that all the dependencies are exercised and made sure everything's working correctly. So this is where the interfaces, and if they're talking correctly, the communicating correctly with each other or not, is tested. So once the functional requirements are all met, then we go with the non-functional requirements. This is where we look at things like performance, security, load testing. So all of those are non-functional requirements. But then there could be some of those requirements. So specific test cases are written in order to test those requirements. Then we have to make sure that a record is kept of all of the test cases and the outcomes, the testing activity. And then these steps are basically repeated until the whole system is tested. So our primary goal here is to identify any failures in this current component configuration that we have, because we don't want to take it forward until and find out when the entire system is built. We want to identify those failures between the interaction of any of the subsystems as soon as possible. So that's our primary goal. And then as more and more components get added, we basically repeat this process. So that's the process followed in integration testing. That's all in this video. In the follow-on video, we'll look at system testing. Thank you.